Thanks for coming. I'm a new postdoc at IAS, and I just got my PhD from MIT. Major focus of my work has been on understanding the geometry of certain polytopes that arise in combinatorial optimization. So in fact, one could make the argument that polytopes are maybe the central object of study in combinatorial optimization. These objects arise for either direct reasons in things like linear programming, where our goal is to optimize some linear function over a polytope, or they can arise indirectly as a continuous relaxation, an object that helps us reason about some associated discrete object. For example, sometimes we can understand graph-theoretic properties through defining an appropriate polytope. In fact, what I'll focus on in this talk is a particular family of polytopes called the unit congestion polytopes. And I'll give an informal definition for now, which is that really these family of polytopes, their goal is to try and capture routing problems in some communication network. It's in fact a little bit notationally involved to really define this formally, but what instead I'll do is I'll give you some motivating example, the goal of which will be to try and explain to you an example type of optimization problem that this polytope is supposed to capture. OK, so suppose we're a content provider, say Akamai, and we have a small number of data centers distributed throughout some gigantic communication network. This is actually a dandelion drawing of the internet backbone. We could imagine that maybe we want to support some sort of communication among these different data centers, and we want to use this underlying communication network. So really, the types of problems that I'll focus on in this talk are communication problems which are defined by a vector. The indices in this vector, they represent different pairs of terminals that want to communicate. And really, you can think of the entry in that vector as a scalar value for the target rate that you want to support communication through. So the goal is to figure out some way to map these rates to flows in the graph. We could imagine, this might be one candidate routing solution. Well, we've mapped this target rate of value x to some flow, where the value of this flow is equal to x. And similarly for the other ones, we have a set of paths that have flow value y and z for the teal set. And in fact, this is now where we're going to encounter an optimization problem. There are many ways of mapping this vector of demands to some sort of routing solutions which support these communication requests. And in fact, what we'll focus on is a type of optimization problem which attempts to not overload any link in the network too much. Like here, for example, we have one link in the network where there are many different paths using it. We can imagine this is a very congested link where really the total rate or the total flow that we're sending in this routing solution is very large compared to the intrinsic bandwidth of the link. So instead, we might try a different routing solution, which really the worst congested link is less congested than in the previous case. So really, this is a type of optimization problem called the min congestion routing problem. And there's a formal definition hidden in here someplace. But really, you can think of it as a min-max optimization problem. The goal is to try and minimize the max over all edges of the congestion. Is given the set of demand vectors to find some flow which achieves as small congestion as possible. And really, it's attempting to try and maximize throughput to finish this communication problem as quickly as we can. So the unit congestion polytope for some graph and some set of terminals is just the set of vectors that we can route with congestion at most 1. It's the set of vectors which there is some good routing scheme for. And what I want to make are the following points, which is that the standard view of this polytope, it's some set of vectors in some low-dimensional space, is that it's easy. Typically, we think of this polytope as being easy because we can actually compute facets efficiently. We can set up, given some candidate demand vector, we want to figure out if it's inside this polytope or not. Well, we can set up that decision question as a linear program, and we can solve it in polynomial time. We can find some vector of flow paths that actually realize it, or we can find some facet that proves that it's not inside the polytope. And typically, given that this is an quote-unquote easy problem, well, the main application of this in approximation algorithms is using it to approximate some hard problem. Usually, we hope that this polytope, which we again think of as easy, well, we think it's a good approximation to some hard polytope. And we care about the relationship between, say, flows and cuts. We think of maybe, for an easy polytope, if it's multiplicatively a good approximation to a hard one, in terms of, say, Banach-Mazur distance, then what we really get as a consequence is that optimizing a linear function over this easy polytope is actually a good proxy for optimizing the same linear function over a hard polytope. So the standard view is to only care about the geometry of this polytope as it relates to the geometry of some hard to optimize problem. But in fact, you could ask, are there more to say about these polytopes? What if we just care about the geometry of these polytopes for other reasons? In fact, there are very basic questions that are sort of unanswered about these types of polytopes. And one that I'll focus on in this talk, which I've spent a while thinking about, but there are many more to be asked in this domain, is there a much smaller approximate representation for these polytopes? The way I've defined it right now, how many numbers do we need to really define this original polytope? We have to specify the entire gigantic graph, and we could ask if there's a much smaller approximate representation. And what I mean is maybe there's just some much smaller network on just those 4 terminals that captures all the relevant communication properties of the original network. Maybe there's just 4 choose-2 numbers, just the values of all the direct connections in that smaller network, and that's all we really need to do to understand how these different terminals can communicate using this underlying communication network. And just to explain this approach a little bit more in detail, what that would really mean is that there's some way of simulating this smaller network in the original one. There's some way of mapping each of these edges to some set of flow paths in the network. This edge between A and B is mapped to this, this flow path here, and similarly for all the others. But now what we could hope to do is we could hope, if we're given the original optimization problem we want to solve, we could instead solve it on this smaller network that is hopefully much smaller. And if we had an optimal solution to it, well, this would already give us a good solution in the original network. We could just simulate that solution using our simulation of the smaller network in the bigger one. And what I want to highlight here is it's not surprising that this is a strategy. There's always some way of finding a smaller network that you can simulate in the larger one, and maybe you're doing a little bit worse in this way. What should be thought of as maybe a little bit surprising is that there's one fixed smaller network that'll work no matter what communication problem you want to solve. If you give me the graph and give me the set of terminals, there's one smaller network, one fixed way of mapping solutions back to the original one, which is provably good no matter what problem you want to solve. So that's really a geometric statement if you think about it. It has to do with how linear the original polytope is. And these types of understanding the geometric properties of these polytopes can actually have stronger algorithmic applications. If we don't just care about what can be solved in poly time, we care about really how fast can we do it. Well, we can imagine that this representation, the one I've described for you, it saves space first because you could store this much smaller network, and you can run your algorithms directly on that graph instead of the original one. So the focus, a lot of my work is on understanding geometric properties of these easy polytopes and figuring out how we can exploit them better to get faster algorithms. So I'll mention just a few results along this line, then I'll talk about the many, many open questions, which is, so first, actually you could ask how good an approximation factor can you get between these? How well can I condense out the communication properties of the original network? You can actually get an approximation factor which is independent of the size of the original network. It actually doesn't matter how massive the internet backbone is. It only matters how many different blue terminals you have. And in fact, it depends even better than logarithmically on those number of terminals. You can also prove things like if you require yourself to represent the communication properties on a smaller network, actually there's a lower bound of square root of log k, so there are many interesting questions trying to understand what the true answer is here. But in fact, for some notion of simple graphs, this even improves to some universal constant. So it doesn't depend on the size of the network, and it doesn't depend on the number of terminals. And this is true for things like planar graphs, which arise in road networks. And it's true for graphs of bounded tree width, which the internet backbone is known to have bounded tree width. And it's even true for graphs with the so-called padded decomposition property. Roughly means graphs which have small separators at every scale. So for all these graphs, there is a smaller representation. And the last thing I'd like to talk about is that there are really many more questions that I'm interested in working on in this, is that it seems like in a lot of cases in TCS, we've stopped once we've said that the polytope is easy to recognize. Once we know the facets are easy to compute, we don't say anything more about what they actually look like. But knowing an algorithm that can compute the facets doesn't tell you everything you might want to know. So actually, in the case for just a small number of pairs of terminals that want to communicate, well, understanding the flow properties, these are all classic results in combinatorics. You get things like the min-cut max flow theorem. And really, those types of theorems, they tell you that cuts characterize flows. That whether or not a flow is routable with congestion at most 1 is really just you check the obstructions for cuts. And if those cuts are satisfied, then the flow works too. But what's interesting is that it's well known that for 3 commodities, for 3 pairs of communicating terminals, cuts don't characterize flows anymore. And what we do with this problem, that cuts are not a perfect characterization of flows, well, really, people have gone in different routes for this. So most approximation algorithms literature deals with this problem by asking how well do cuts approximate flows, because they think of flows as easy and only being useful in how well they can approximate a hard problem, like graph partitioning. And graph theorists sometimes care about what families of graphs do cuts equal flows. Of course, just understanding this polytope for even a small number of commodities should be interesting in its own right. We could ask basic questions like, for the example I gave you where there were just 4 terminals, but the graph was gigantic, is the number of facets of this polytope small? If we thought about just cuts that separate these different pairs of terminals, then there'd be an easy way to upper bound the number of facets, and it would be finite as a function of just the number of blue nodes. But in fact, for this question of how many facets there are in the flow polytope, the best upper bound I have is actually doubly exponential in the size of the original network, which could conceivably be gigantic. In fact, there are other questions you could think about, like actually really the directions that facets point in. Well, they actually represent different trade-offs that you can achieve between different flows. Once you're on some facet of this polytope, well, moving along that facet doesn't change the fact that you have a good routing solution. So it tells you what sorts of trade-offs between the different commodities you can achieve. And in fact, I think that one should be able to classify these types of facets, that at least for the case of 3 commodities, there should be some universal combinatorial characterization of what directions the facets point in. That more than just the number of vertices being finite, I think there are only a finite number of directions that can really arise in these polytopes. And this would lead the way to other sorts of algorithmic applications. You can try strategies if the number of facets are finite that you could never do otherwise. Like instead of when you're trying to find approximately is there a point inside the polytope, you don't just need to move in that direction and keep binary searching until you hit it. You could instead shoot a ray in some other direction and walk along the facets until you hit the right point. But that wouldn't be a good strategy if the number of facets was really prohibitively large. So that's about all I wanted to say about this. Can I answer any questions?
Thank you very much. Questions?
Avi?
Is the notion of polytope sparsifier a good
For
definition even?
a sparsifier?
Sparsifier of polytopes as opposed to graphs.